When I show you a picture like this, you can instantly and automatically make all kinds of inferences about properties of the item that aren't displayed in the picture. For instance, it's called a frog, has internal organs, it can move, it can grow, it likes to live in the water, it will reproduce, it breathes air, all kinds of things. And what's more, if I give you a very different kind of stimulus, like this one, you can make many of the same inferences about the item that the word denotes. And the question is, how do our brains support this cognitive ability? In the late 19th century, the great German neurologist Karl Wernicke proposed an answer to this question. Wernicke knew that different regions of our brain are dedicated to the representation of different kinds of sensory, motor, and linguistic information. And he proposed that general knowledge about the world is coded in learned associations amongst these different representations. So, for instance, when you hear the word frog, you might represent it with patterns of activation in perisylvian areas of cortex. But that activation will propagate to other brain areas that code different kinds of information. So, for instance, you might activate representations of the object's shape in the inferotemporal cortex, or its color in neighboring regions. You might represent the way it moves with patterns of activity in middle temporal cortex. You might represent the sounds that it makes, or your emotional response to the stimulus, or the actions that you might wish to take in response to the item by activating other representations distributed throughout the brain. And Wernicke really thought that those associations were encoded in a distributed network that really ran all throughout cortex, so that there was no single place where the meaning of the word or the object might be stored. And on the basis of this idea, he predicted that one should never see an impairment that selectively disrupted our general knowledge about the world. This prediction was disconfirmed in the mid-1970s, when Elizabeth Warrington described just such an impairment in a syndrome that has since come to be known as semantic dementia, a progressive disorder that gradually erodes everyday knowledge about the world while leaving other cognitive abilities remarkably intact. In the 1990s, John Hodges and Carolyn Patterson documented 3 remarkable aspects of this syndrome. The first is that the dissolution of knowledge in the disorder is not arbitrary, but is highly structured. For example, in one study, a patient with semantic dementia was asked to name line drawings of common objects and animals. This table shows the responses he gave to various different kinds of birds in the set. In his first session, the patient correctly named the bird, chicken, duck, and swan, but produced incorrect names for the eagle, ostrich, peacock, penguin, and rooster, calling these items either a duck, a swan, or a chicken. 6 months later, he was unable to get any specific bird name out, with the sole exception of the word chicken. All of the other items were called bird. 6 months later, no specific bird name was produced, and for the ostrich, peacock, and penguin, the incorrect response cat was generated. And 6 months after that, the word bird was not produced for any item. Instead, the patient called several of the birds animal, produced the incorrect response dog and horse for some items, and even very occasionally made very unusual responses, such as calling the peacock a vehicle. We see 2 general patterns in these responses. First, we see confusion of semantically related items. When incorrect names are produced, they tend to refer to similar kinds of things. In this case, other birds, or later on, other kinds of animals. Secondly, we see a loss of relatively specific names, but preserved knowledge of more general names, such as bird and animal. The second remarkable finding is that this pattern isn't restricted to naming or to verbal report generally, but it's observed across all testing modalities. To see this, consider the following drawings produced by one patient with semantic dementia. In the first case, the patient was allowed to observe a model drawing while he produced a copy of it. And you can see here that the drawings are fairly recognizable as a camel, a cow, and a duck. In the second case, the patient was allowed to consult the model drawing, but then it was removed, and the patient was asked to draw what he had been looking at from memory 10 seconds later, and he produced drawings that looked like this. What you can see is that the items aren't completely unrecognizable. Indeed, they're recognizable as animals, and they have particular parts that are recognizable, like eyes, mouth, tail, legs. What's missing are any idiosyncratic details that would allow you to understand which kind of animal you're looking at. The udder of the cow, the feathers on the tail of the duck. These properties are missing, as though the patient has lost information about the visual properties of objects that differentiate conceptually related things, just as they have lost the names that individuate conceptually related things. The third remarkable fact concerns the nature of the pathology observed in the disorder. Wernicke might have explained the pattern that we've just described as arising from a kind of global pathology throughout the brain, since he believed that the associations amongst different kinds of representations were really very widely distributed in the brain. But that is not, in fact, what we see. This figure shows regions of gray matter atrophy in 2 patients with semantic dementia. Anywhere that the image is colored orange shows places where the patient had less gray matter than other age-matched healthy adults in the sample. And what you can see is that the pathology tends to be concentrated in the anterior part of the temporal cortex, more pronounced on the left, but if you look closely you can see that there's pathology in both the left and the right hemispheres, which is the characteristic pattern that we see in semantic dementia. So on the basis of these observations, we proposed a different hypothesis. Specifically, that the interactions between different sensory motor and linguistic representations in cortex are mediated by a single cross-modal hub situated in the anterior temporal cortices bilaterally. On this view, when a stimulus such as a visual image appears in the environment, activation first propagates toward the anterior temporal lobe hub and then is broadcast from the hub toward other associated sensory motor and linguistic representations distributed throughout cortex. For us, the question then was, can this hypothesis explain the patterns of impairment observed in semantic dementia? To answer this question, we turn toward a neural network model of the hypothesis. Neural network models are composed of simple neuron-like processing units, which can adopt activation values that range from 0 to 1. The activations are analogous in some respects to the mean firing rate across a population of neurons. Each unit receives signals from other units in the network by means of weighted synapse-like connections, and each unit also transmits information about its state to other units in the network by means of weighted connections. The connection weights can be excitatory, so that activation in the sending unit promotes increased activation in the receiving unit, or they can be inhibitory, so that increased activation in the sending unit promotes deactivation of the receiving unit. The weights can also vary in the strength of their effects. Each unit thus computes a simple function. Across the sending units, it adds up the activation of the unit multiplied by the value of the interconnecting weight plus a constant bias term to get a total net input. It then adjusts its own activation in response to the net input, with positive inputs pushing the activation toward 1 and negative inputs pushing the activation towards 0. In a neural network model, collections of units are wired together in the manner stipulated by the hypothesis under investigation. In this case, the model implements the semantic hub hypothesis. Visual representations of objects and representations of verbal statements about objects interact with one another by a common set of hub units which serve as a model analog of the anterior temporal lobe. A computer program is then used to simulate how patterns of activation will flow through such a network given this pattern of connectivity and specific values for the interconnecting weights. Initially, the weights are set to small random values, but as the network processes different patterns, the weight values are adjusted to encode associations amongst words and images that occur in the model environment. Here's what the model looks like in the software interface. Each small rectangle stands for a single model unit. Units down the left individually represent familiar words, including the names of objects and also other words that we might use to describe them. Units in the top right encode visually perceived features of objects, so that the visual appearance of an object is coded with a pattern of activation over these units. Wherever an arrow appears, this indicates that all of the units in the originating layer send weighted connections to all of the units in the receiving layer. In this case, all of the word and image units send connections to and receive connections from the hub layer, as proposed by the hypothesis. Here we see model behavior in the early phases of learning. Each unit is split in half, with the left side showing the activation generated by different inputs, and the right half showing the target activations, the patterns that should be generated if the model is performing correctly. You can see that with each input, activation spreads weakly throughout the network and quickly dies away. The model never generates the correct response. With each presentation, however, the interconnecting weights are adjusted by tiny amounts to make the generated pattern just a little bit more similar to the desired pattern. Here we see model behavior later in learning. After extensive learning experience, the model can eventually generate the correct patterns across all word and image units in response to any kind of input. Given a name, it can generate a correct verbal description or a visual image. Given an image, it can generate a name or a verbal description, and given a verbal description, it can generate a name or an image. In this sense, the model embodies Wernicke's basic proposal that knowledge about meanings of words and objects can arise from learned associations amongst different kinds of representations, in this case, representations of words and images. However, the associations themselves are encoded within a single cross-modal hub. The trained model can then be used to simulate behavior on many of the tasks that we use to assess semantic knowledge in patients with knowledge impairments. To simulate picture naming, for instance, we provide the model with an image. Specifically, we directly activate the visual properties that correspond to the familiar item. We then allow activation to propagate all through the network and inspect the activation that emerges across the name units. In this case, the model has activated a single unit corresponding to the name sheep. So we count this as a success. The model has named the image as a sheep. To simulate naming of a different item, let's say this eagle, we simply input a different activation pattern over the visual units corresponding to the learned pattern for eagle. We allow activation to propagate throughout the network and inspect the activation over the name units. Here, the model has produced the word eagle. And here, it produces the word iron. Of course, we don't need to only test it on naming. We can also assess the model's ability to comprehend spoken words simply by providing direct input to the single name unit corresponding to a familiar item. Again, we allow activity to propagate throughout the network, and now we inspect the pattern that arises over the visual units. In this case, the model generates the same pattern that it's learned to represent the visual appearance of an eagle. And here's the model comprehending the word iron. Again, it generates the visual pattern corresponding to the iron in this modeled training environment. With the trained model showing good behavior, we can now assess whether the general hypothesis can explain the patterns of impairment that we've observed in semantic dementia by simulating the effects of the disease in the model. Recall that the pathology in the disorder tends to be concentrated in the anterior temporal lobe, that is, in the hub layer of the model. To simulate the loss of neurons in this region, we therefore remove some proportion of the weights entering or leaving the hub layer. We can then assess the behavior of the damaged model on the same kinds of tasks that we use with patients: picture naming, word comprehension, and so on. Let's see what happens when we ask the damaged model to name a picture of a sheep. activation spreads throughout the network. The model initially begins to activate the sheep unit, but activation quickly dies away on that unit, and as you can see, it has produced the incorrect name, pig. Here's the damaged model naming the cat. It gets that correct. Here it names the dog, again correctly. And here it names the eagle. Recall that the healthy model produced the name eagle in response to this image, but the damaged model has produced the name bird. Here it names the train correctly. But here, when given the sled as input, rather than producing the word sled as output, it produces the word motorbike. The impairment is not restricted to naming. Here we provide the model with the name eagle as input. In response, it generates an incorrect visual representation. Some of the eagle's features are missing, while other properties are incorrectly added in. We can simulate more severe damage in semantic dementia simply by removing a larger proportion of the weights entering and leaving the hub layer. Watch what happens in the name layer when the more severely damaged model is given the car image as input. Although it begins to activate car, this activation dies away, and the model instead weakly activates the response vehicle. Here it's given a lorry visual image as input, and it correctly generates the response lorry. Here we again provide the model with the sled as input. Recall that under milder damage, the model produced the response motorbike to this input, but under this more severe damage, what we see is that it's unable to generate any name at all, consistent with the response, I don't know what that is. In summary, when we damage the model, what we see are the same kinds of errors that we see in patients with semantic dementia. Semantic errors, where the incorrect name of a related kind of object is produced. Ordinacy or level errors, where the model is capable of producing a more general response that's technically correct, but not at the same level of specificity that it usually produces. And, especially with increasing brain damage, no response errors, an inability to activate any name at all. Other errors, for instance, producing completely unrelated responses to a given input, are rarely or even never observed in the model. The remaining question is, why does the model exhibit these patterns? The answer has to do with the nature of the patterns that arise across the hub units after the model has learned. It turns out that these patterns express the degree to which different items in the environment are conceptually similar. That is, similar kinds of things evoke similar patterns of activation over the hub units after the model has learned. Thus, for instance, the various different birds all evoke quite similar patterns, the various different mammals all evoke quite similar patterns, and so on. The pattern of activation that arises in response to the eagle can be viewed as a point in a high-dimensional representation space. Other birds evoke similar patterns to the eagle, and so correspond to nearby points in the same space. Other kinds of animals evoke somewhat similar patterns to the eagles, and so are somewhat close in the space, while unrelated items, like sleds and irons, are represented with very different patterns, and so lie very far away in the representation space. Now consider what happens when the model must name the eagle. Other birds that are conceptually similar to the eagle, hawks, falcons, vultures, and so on, are represented with similar patterns, but they have different specific names. So, to get the answer correct, the model must evoke exactly the right pattern across the hub. Any distortion of the pattern as a consequence of disease will cause the model to confuse the eagle representation with nearby patterns, thus producing an incorrect specific name. However, the name bird applies to all of the eagle's representational neighbors. Thus, if the eagle pattern is mildly distorted due to brain damage, the model can still generate the bird response. Likewise, the name animal applies to all of the birds, and also to all of the neighboring mammals. So, even when the eagle pattern is grossly distorted as a consequence of disease, it is likely to be able to generate the animal response. In other words, both the tendency to confuse semantically related items and the relative preservation of more general information about objects arise in the model because the patterns of activation that arise across hub units through learning end up expressing the degree to which different items are conceptually similar.